Okay, now the MDE video goes into detail on this. This is from the MDE class. We're not gonna go into all that. Okay, first thing is, we're gonna talk about compound interest because it's a paradigm example of an exponential function. Everybody needs to understand for their financial future, if nothing else. $1,000 at 10% annual interest. Okay, what's that mean? And we'll ask everybody to write down how much they would have at the end of the year. And over half the class didn't write that down. Okay. So this tells me maybe people don't relate the percentage, or maybe you just can't do things quickly. But what would it be? What's 10% of 1,000? Can you write down what 10% of 1,000 is? Just write down the number. What's 10% of 1,000? Okay, now we still having some trouble with this, but 10% of 1,000 is 100. 10% means 10 per 100. Okay, you have rules, but maybe this is. I think we get this in middle school, but okay. So we have to understand that 10% of 1,000 is 100. Not going to do that calculation, but if you go back to the MDE class, you get more detail. If we add $100 to 1,000, how much do we have? Can you write that down? Adding 100 to 1,000. Yeah. Okay. Well, everybody got that? Okay, now what's 10% of 1,100? Okay, I think maybe we're oriented enough. So we know that after 1 year, we're gonna get $100 interest on $1,000. We're gonna end up with 1,100. Then in the next year, we're gonna get $110 of interest and add that to the 1,100 to get $1,210 and so forth. And that's going to continue. And the amount of interest we get every year keeps increasing. And the amount of interest is proportional to how much money we have. And that's the key to an exponential function. When an exponential function grows at a rate that's proportional to how much you've got, when a function grows, when a quantity grows at a rate that's proportional to how much you've got, then you get an exponential function. Okay. If it's a population, if you have a good environment where there's plenty of room for the babies to grow, really think of Tishan's babies, but you are going to grow at a rate that's proportional to how much you've got. If you got a herd of 1,000 guppies, no, you wouldn't call that a herd of fish. If you got a herd of 1,000 cattle, okay, and maybe that grows at a 10% rate. So in a year, your population going to increase by 10%. Okay, I mean, of course, your birth rate has to exceed your death rate. Cattle do die, especially eating them. But they don't live all that long either. Okay, point is, if you have a herd of 2,000 cattle, then you expect to get twice as many new cattle at the end of the year. So if your cattle, if 1,000 cattle grows up to 1,100, then you expect 2,000 cattle to grow up to 2,200. You expect to get twice as many new heads of cattle. Okay, it's proportional. Well, so that's gonna lend itself to an exponential model. A little hard to wave my hand and say that without writing things out, but there it is. Okay, now the key that you have to see is this, okay? What's A plus 0.10 A? Well, you factor A out, you get A times 1 plus 0.10. And hopefully everybody understands that, but if not, just use the distributive law. A times 1 gives you A times 0.10 gives you 0.10 A. So this can be written this way. And of course, then 1 plus 0.10 is 1.10. So what we're doing here is we're adding 10% of A, okay? A plus 10% of it. But that's the same as multiplying by 1.10. You need to understand that because that's going to lead us to the form of an exponential function. Okay, well, cutting this stuff from this stuff. Now here is 0. We have amount $1,000. What's our new amount? Well, we're going to add 10%, which means we're going to multiply $1,000 by 1 plus 0.10, or multiply by 1.10. So to get the amount at the end of the year, we multiply 1,000 by 1.10, giving us the 1,100 that we get if we calculate the interest separately. So we just kind of shortcut the process by multiplying by 1.10. And that's going to allow us to build up these expressions as we'll see in a minute. Okay, so then at the beginning of, or at the end of year 1, you're going to have 1.10 times $1,000 is what we have. There is the new amount. We'll go here. Okay, and then we want to see what we get that year. Well, we multiply this by 1.10, and we get the amount for the next year. So we multiply 1.10 times 1.10 times 1,000. Isn't that the same as 1.10 squared times 1,000? Yeah. Okay. And then we multiply that by 1.10, and we get 1.10 cubed times 1,000. When we multiply that by 1.10, we get 1.10 to the fourth. Every year we multiply by 1.10. So after 4 years, we will have multiplied by 1.104 times, meaning that we would have 1.10 to the fourth times 1,000. So what do we have at the end of 20 years? We don't have to do it year by year since we've got our compacted notation. We see that the exponent we get for every year matches the number that year. So we end up with 1.10 to the 20th times 1,000 equals 7,000. Now our exponential function, our amount as a function of t is then 1,000 multiplied by 1.10. T is the number of years. It's going to match the number of times we multiply by 1.10. Well, you recognize that as an exponential function. That's AB to the T. A is 1,000 and B is 1.10. Okay. Now, if I can find it here. If we were to compound twice each year, what's that mean? It means after 6 months, we get half of our interest. Okay. Half of our interest would be 5%. And then at the end of the year, we get 5% of that. Okay. See the 5%, well, the amount we have at the end of 6 months is more than we started with. So we're getting 5% on a little bit more money, so we end up with a little bit more money at the end of the year. Turns out we end up with about $2.50 more. Calculated in here somewhere, I wrote it down, point to it if I could find it. Geez, I know I wrote it down. Well, it doesn't matter. Okay, now the point is, each time we apply the interest, we multiply by 1.05. I'm not going to give you 10% twice each year. I'm going to give you half 10% twice each year. Okay, and the second half is based on what you have after the first half, which is a little bit more than you had at the beginning of the year. This means that in 20 years, I will have multiplied by 1.05 40 times. That's twice each year. So I end up with 1.05 to the 40th times 1,000. So I end up with general function A of t equals 1,000 times 1.05 raised to what power? Power has to be 2t because t is a number of years. And every year, I'm compounding twice. Means in t years, I will have multiplied by 1.05 2t times. Just another exponential function. But there's a little bit of a complication. Well, your general expression for the amount after n years, if we look at what we've got here, A of 20 is 1.05 to the 40th times 1,000, okay? Hopefully we understand that. And that's 1 plus 0.05 to the 2t, which of course is 1.05 to the 2t, but I want to see what our formula looks like. Okay, so there's a formula. We want to understand the formula rather than just wrote using the formula. Okay, so you got 1 plus 0.05 to the 2t. Why is it 1 plus 0.05? It's because we divided our 10% in half. So the 1 plus 0.05 is 1 plus 0.10 over 2. That's why it's 0.05. And why 2t? Because we're compounding twice each year. So we're going to compound 2t times in 2 years. In general, if we have a rate, instead of 10%, we have some other rate. Maybe it's 4%, be 0.04. Maybe we're compounding it 12 times a year. We divide the rate by the number of times we compound, and that's what you get every time, every short period. And how many times we do that? We do that n times in t years. And then that's times 1,000. Well, that's basically the formula that you see in your text. I think it looks like this, except they just use A. I'm using A of t, that's function notation. That means the amount after t years. And formula I just read down is 1 plus r over t to the nt times t, which is the amount you had initially. That'd be $1,000. Okay, so if r is 10% and you're compounding twice a year, you do 10% divided by 2, which is 0.10 divided by 2, or 0.05. So this is your 1.05. And your n is 2, so you do 2 right here. There's your function. And I did a little bit more with it. But then, and this is something we will actually do until next week. I'm going to give you a preview. We want to know how long it takes this money to double at 10%. So if we have our original function A equals 1,000 times 1.10 to the t, that's what we get if our rate is 10%, compounded just once every year with an initial $1,000. If it doubles, starting at $1,000, we get $2,000. Okay. So we want to find how long it takes to get $2,000. We just set this equal to $2,000. Here it is, equal to $2,000 and solve for T. Of course, you don't know how to solve that for T, unless you have, of course, exponential functions for all of these. And even if you did, you might have forgotten. So here's the equation. This says this is our amount after T years. It's 1,000 times 1.10 to the T. We want to set that equal to 2,000 to find out the T that it takes to get to 2,000. Now, at this stage, we do the obvious thing. If you look at this equation, the obvious thing to do is divide both sides by 1,000. That makes everything simple. We divide both sides by 1,000. We get 1.10 to the T equals 2. That's an equation that's easy to solve if you know the rule. Now, we want to develop the rule. We want to see the meaning behind all this, but I'm going to just cut to the rule. Our rule is A equals B to the C is equivalent to log base B of A equals C. You don't know what log base B means, but you will very soon. Okay, that log base 2 is just the inverse of the 2 to the x function. So you just switch the columns of your basic exponential function and you get your log base 2 function. Okay, log base B. Imagine you have a table for B to the T. You switch the columns and you get the log base B function. And your calculator has built in a log base, a log function. Okay, just one more thing you need. So the stuff about logarithm and solving these equations turns out to be pretty easy compared to some of the stuff that we've done already. Okay, so A equals B to the C is equivalent to log base B of A equals C, whatever that means. Don't worry about what it means. I told you a little bit about what it means, just so you kind of related, but we're going to build that up a little more slowly. So if A equals B to the C is equivalent to that. Meaning, this is the form. A equals B to the C. Now, A is 2, it's on the other side of the equal sign, but that doesn't matter. The thing you can focus on, where's the exponent? Okay. T is your exponent, so C is going to be T. B is the base of your exponential function. That's going to be your 1.10. And A is the thing on the other side of the equal sign, that's 2. Okay. So you're going to learn that we simply identify the A, B, and C here, and then we write it out in this form. So that A equals B to the C becomes log base B of A equals C. In this case, A is 2, so you're going to put a 2 in parentheses here. B is 1.10. That's a subscript. It's not something that's multiplied by 2. It's a subscript that identifies which logarithmic function you have. If you put that here, and then C is on the other side, that's T, and look what we got. T equals this. We solved it for T. Now you probably want to get a number out of this, okay? That's where your calculator comes in. You can't calculate that anymore than you can calculate 2 to the 1/2. 2 to the negative 1/2 would be even worse. Okay? There's a rule that says then that the log to the base B of a number is the log of that number divided by the log of B. Very simple rule. Write it over here. And to get the log, take your calculator, you got a log key, and your punch buttons. Then you get T equals approximately 7. Now, since we've kind of gone over the whole thing, got a question about continuous compounding, which I did kind of quickly at the end because that question came up about the time you all needed to come in. Okay, so I did this quickly, probably doing it when somebody came in. Continuous compounding. If your rate is R, for example, R is your rate, okay? In the example we did, it was 10%, which would be 0.10. Okay. We compound this thing twice a year, we get a little bit more money than if we compounded it just once a year. We calculate 4 times a year, we get a little bit more there. We cut our 10% into 4 pieces and do that 4 times a year. And each time we do it, we have a little more money than we would have had if we were doing it 2 times. Okay. Or we could do it 12 times a year, once every month. We do it 52 times a year. Each time we get a little bit more money. Okay. Now, going from 12 times to 52 times, we don't get all that much more. Okay. We go to daily, we do it 360 times. Usually banks use 360 for a year instead of 365 with a quarter or whatever it is. Why not just do it continuously? Well, we talk about what that means is, but that means every instant you're doing this thing. You break your 10% into an infinitesimal amount, but do it an infinite number of times. And that's what gives you e to the RT. So, what first thing you got to understand is that if you compound it continuously, this is what it looks like. Okay, that formula doesn't work anymore, but this is a limit what that formula tells you. We'll talk a little bit about that to help you anticipate limits. Okay, here's your formula. E is just a number. Not going to explain it to you now, but I will explain it probably later this week and next week. Okay. Actually, I can't do it later this week. I'm not here at first. Got research days. I'm doing some stuff with research days that you might actually find helpful. Okay, anyhow. We have this. So we have A equals 1,000 e to the 0.10 t for this function if the interest is compounded continually. Well, we just translate this to the form e to the 0.10 t plus 5. Just okay. We want to find t when the amount is 5,000. That which means we want to find how long it's going to take before we got $5,000. Okay, I'm guessing it'll be about 16 years. So if we want to find when the amount is 5,000, we're going to set 5,000 equal to 1,000 e to the 0.10 t. There's our equation. We divide both sides by 1,000, we get e to the 0.10 t plus 5. And now we have the form a equals b to the c. C is your exponent. That's not 0.10 t. That's your exponent. We identify your base, which is e. Base is e. And your a is on the other side of the equal sign, it's 5. And then we just plug that in to this form. B is e, so it's log base e. A is 5, and C is 0.10 t. We do that, there's our equation. The thing that we want to understand about that equation is, now it's good to know what E is, it's important to know. But we don't actually have to know what number to put in there for E, especially since E is an irrational number, you never have it exactly right. Log base E is the natural log. E is somewhere between 2 and 3. We'll see how that works out. All you really need to know to solve the equation, though, is you got a natural log feed on your calculator. Log base E is a natural log. And we solve this very easily using the same rule we used over there that I haven't explained or anything, but natural log of 5 over 0.10. . 10. And, you know, when I did that, I don't know, I was thinking I was hurrying. And that was not right. Actually, that's right. I don't know. It's natural log of pi over 0.10. We just solved this. We divide both sides by 0.10. Your calculator tells you what the natural log of pi is. Okay. Only about 1.6. There you get your result. Now that's where we're headed this week and into next. I'm gonna have to rearrange assignments slightly because we're not here on Thursday. Let's see what we can get done today. Okay, just briefly reviewing what we already talked about. I would call this. Okay. Okay, generally, we can look at the use of X and Y. We're gonna start with Y equals B to the X. You're familiar with Y equals 2 to the X. Looks something like that. That's pretty badly drawn, but there it is. So here's Y equals 2 to the X. Here's Y equals 1/2 of the X. One to the X, 1 to the X is always 1. That's right. Y equals 3 to the X. I'm gonna call it for that one. First graph will be made a lot more carefully. Here's Y equals 3 to the X, and Y equals 1/3 to the X. But then you have Y equals E to the X between the 2 to the X and the 3 to the X graph. Because E is between 2 and 3. It's a little closer to 3 than it is to 2, about twice as close to 3 as it is to 2. And E is just a number. E's limit is n approaching infinity of 1 plus 1 over n to the nth power. This is just compounding 100% interest n times. If you got 100% interest instead of 0.10, you just got 1. 100% is 1. You divide the 100% by the number of times you compound it. And then you do that n times. And that gives you your interest for a year. At least your multiplier for a year. If that approaches infinity, that means you're breaking this thing up more and more times every year. And applying that interest that many times. So maybe n is a million. Maybe you divide your 100% interest into a million parts and do it a million times in a year. Same thing we just talked about. If n approaches infinity, this approaches the number e. First 11 digits and digits of e are these. And interestingly, it looks like it's going to repeat 1828, 1828, but it doesn't repeat. Okay. Non-repeating. Now, bottom line is, you see that this is about twice as close to 3 as it is to 2. So if you're doing a graph of e to the x, it would be between the 2 to the x and the 3 to the x graph, probably somewhat closer to the 3 to the x. Okay. So this kind of gives you a picture of exponential graphs. You can have an exponentially increasing graph and have an exponentially decreasing graph. Okay. Exponentially increasing graphs are things like populations, interest, value of an investment, and many other things. Exponentially decreasing, I think I might have mentioned this before. You're taking some kind of medication, your body tends to exponentially decrease the amount of medication in your body, which is why I keep taking doses. So you build up gradually a sufficient amount of the antibiotic in your body without poisoning yourself and without having the amount decrease to the point where whatever's infecting you or whatever you're trying to treat is being treated. Okay. So exponential functions are very important in almost every field. Actually, they pretty much govern the universe, but when you get into the function of the complex variable, you don't necessarily understand how or why. And that's a pretty advanced topic that very few people ever get to. Okay. Don't really need it unless you're going to be an engineer or scientist. Okay. So anyhow, if I want to graph an exponential function, well, we can transform. A transformed exponential function with phase B. Transform function be A, F, and CX plus K. We don't generally do a horizontal shift on an exponential function because we take care of that with this number sheet. Number C, right? Okay, so let's get a graph. Two to the x function, 24 days of function. Looks like this. You want to graph the transform function, 3 f of x minus 4. Should be able to write down the graph of the exponential function table and graph accurately in a minute or less. You're probably going to have more time than that. I probably ought to stop the video. We're wanting to graph 3 f of x minus 4 with f of x is your basic toolkit exponential function. Okay. Well, what happens is every y value becomes 3 times as great. The y values are represented by arrows from the x-axis up to the graph. So if we triple the y value at this point, we end up here. If we triple the y value here, we end up here. If we triple this y value, yeah, here. We triple this one, well, we end up about here, and that comes right out. So we get functions like this. This would be your y equals 3 times the x. If you made a table, you would find that when y is 0, x equals 3, y equals 1, x equals 6, and so on. It would agree with the picture you get if you do these arrows and construct this thing in the way we enough of time. Then got to do the minus 4. The minus 4 lowers you down 4 units. And y values become 4 units less. Whatever 3 times 2 to the x is, 3 times 2 to the x minus 4 is going to be 4 less. Meaning you go this way with your y value, so that this then would come down about here. This would come down an equidistance. Maybe down to here, and then would come down just a little further than that. At this point, we come down to here. They didn't have a point over here, but I don't have to draw the arrows over there. So you would have the graph that kind of looks like this. That would be this graph lowered down 4 units. So this is graph y is 3 times 2 to the x minus 4. Now we can horizontally shift and stuff like that, but there's another thing that we are generally going to do instead. So let's think about what the graph of y equals 2 to the 3x to be like. Now, to understand the graph of y equals 2 to the 3x, helps to start with a table. There's a rule, and the rule is going to be that every point moves 3 times closer to the x-axis, to the y-axis. Sorry. Okay, so the graph gets squished in this way. Make a table of this function. Want to use numbers -2, -1, 0, 1, 2. Okay. But these aren't going to be x values, they're going to be the values of 3x because 2 is raised to the 3x power. And it's easy to raise 2 to these powers. So I'm going to go ahead and do my values here and then talk a little bit about why we do. Okay, so this is supposed to then be 2 to the 3x. If these numbers are 2 to the 3x, the 3x has to be these values. These have to be values of 3x in order for these, which correspond to these, to be values of 2 to the 3x. So what are my values next? And you know, have an odd denominator. Probably not going to be the easiest thing for you. I don't want to use 2. I didn't want to use a number too much bigger than 2. I'm going to change this function since we haven't really done anything here, but it's up here, here, and here. I'm going to make it 2 to the 4x. Because your fractions are going to be easier. And they're going to be easier to locate on your graph. Okay. I'm going to squash the graph off very good. Okay, so go ahead and make that table. Just write down what I've written down and then tell me what the x values would have to be. Okay, I think I should have a problem. Either because I didn't think so read for the x column, maybe, or because I don't know about the arithmetic. If 4x is 2, what's x? X has to be 1/2. To get x, you would divide 4x by 4, right? So it should be obvious you're going to divide all these numbers by 4. If you do something different and then check, is 4 times this equal to this? Because that's what it has to be. If this is x and this is 4x, then whatever number you get here, you check it out. Is 4 times this number equal to this number? Is 4 times 1/2 equal to 2? Well, let's see, 1/2, 2. Yeah, 4/2 make 2. Okay. And here you have to have 1/4. Here, of course, you have to take 2. This would be -1/4, and this would be -1/2. Make sure you understand that, because you're going to understand this more on it. What to do? So let's put -2 here, 2 here. Like we're walking. Well, I have to here. Here's 4. Here's 2, here's 1. Here's 1/2, here's 1/4. Okay. Now, we need X values like -1/4. -1/4, -1/2. The biggest X values we get are going to be 1/2. So our X values are all between -1/2 1/2. Means the whole graph is going to fit between here and here, whereas the original 2 to the X graph is between here and here. Well, the original 2 to the X graph has points about okay. So we've got -1/2, -1/4, 0, 1/4, 1/2. There are X values. And -1/2 goes with y equals 1/4. That's going to give us a point here. And -1/4 goes with y value 1/2. And 0 is going to go with y equals 1. That's not going to change. 1/4 is going to go with y equals 2. And 1/2 is going to go with y equals 4. So there are the 4 points, 5 points on this graph. And you see if the graph looks like this. Transformation is this point is moved here. This point is moved here. This point stays where it is. This point has been moved here, and this point has been moved here. Every point was moved closer to the x-axis. And I didn't do a good job of making this graph scale, but every point moved 4 times closer to the x-axis, which stretched the whole graph up by a factor of 4. Well, that's what the number in front of the x up here does. That's a transformation that you did in the homework back in chapter 1, but we haven't talked about it because it's not an important transformation until you get to the exponential function. Anything you need to do, you can do to the other functions with vertical stretches, horizontal shifts, and vertical shifts. Here, you need vertical stretches, vertical shifts, horizontal compressions. You can do everything. Okay. So that's something you just need to know about the graphs of exponential functions. That and what you already know about how to do vertical shifts and horizontal shifts and vertical stretches and all that stuff. Okay, talk a little bit about log functions. Log base b of x function inverse to y equals b to the x. So take a table, the y equals 2 to the x, which everybody just did. You get y values 1/4, 1/2, 1, 2, 4. How do we make a table for the inverse of a function if we've got the table for the function? Well, first of all, we've got to make sure the function is 1 to 1. Well, all exponential functions are 1 to 1. So we don't really have to worry about that, but for other functions, you do sometimes have to worry about that, as you should know. Okay. To get the inverse function, we just switch the columns. So we put our -2, -1, 0, 1, 2 in the y column instead of the x column, and then the x column is the y column of the original graph. In other words, we just switch columns. If we graph these two functions, f of our exponential function is going to look something like this. Now, if we grab these points, well, let's see, down here would be -4, so here would be -2. Here's 1, here's 1/2. Here's 1/4. We should understand these. So our point 1/4 -2, x is 1/4, y is -2. X is 1/2, y is -1, and over 1/2 and -1. That would be here. We have the point 1, 0, that's the x-intercept. We have the point 2, 1. To come out to 2, we got to come up to 1. That would be here. Now then, we got to go a little further out here. We got the point 4, 2. Well, let's see, here's 2. So 4 would be on about here. Watch, 2 is about here. So we get a graph through these points. And so this graph is kind of a flipped and rotated graph of this. Okay. You need to make these graphs by hand. Matt's going to ask you to do that. Tex is going to show you how you do them. You know, you want to be reading the text and doing the homework. One thing I'm going to add. Incidentally, if you want to know how you did on the exam, stick around after class, I'll tell you. And if you want to talk about how you did and so forth, we can do that too. Okay. I'm going to advise that when you do your homework, you start writing out your solutions for the problems of open math. Okay. And write out your solutions, please. Don't do those solutions by watching the video step by step and working it out. Digest the video, put your digested stuff away and do the problem. Okay. That's how you're going to learn it best. And then bring that in so I can look at it. If I can see it in class, then it gives me a much better picture of how I need to address any issues that might arise. I can't tell that much by looking at the homework, except if you got half of it done, I can see what half you did. And chances are you probably did that the way you should, because you didn't get the other half. Okay. And you know, I've seen a lot of kind of half done homework. And less than half in some cases. Okay. Kind of take my advice and start doing that. I can help you better if you need it. Now, I'm going to do the next logical thing. I got to remember what that was. Okay, so we've seen what the graph looks like. Open math is going to ask me to do similar things. remember, you can make estimates from the graph. I want to estimate the log of 1.6. Come out to 1.6 here and come up with a function for just over. Remember, you can do that. You know, you could do the same thing for base 10, but we don't have time to do it. We can shift these graphs, expression, do all kinds of things. So I really recommend that you read this section on logarithmic functions. I'm going to have to delay that assignment, but I think I've shown you enough that you should be able to get started on it and do a good bit of it. And I really recommend you do. It's a long assignment. There are 20-some problems. But a lot of them are really easy. A lot of them do just what I showed you. You translate the equation to logarithmic form and punch it in your calculator. Okay. But some of them are more challenging. So try to get the easy stuff out of the way so you understand better what we're going to be able to do in our next class, which unfortunately won't be for a week from today. Now, nice thing about having these research days is there's stuff I can do if you're having problems with the course. I've got this remediation course that I designed. I've learned to do the programming to create the problems. And I should be able to spend most of those 2 days on that. And hopefully I'll have something to be very helpful to you then. Okay,